Here I'm going to go through a 2018 question on acids and bases. This time it came up in one of the options, so I think it's question 11b, where you have an option on the paper to do 2 of A, B or C. It starts off in the usual manner. What is the Arrhenius definition of a base this time? So according to Arrhenius, when an acid or a base dissolve, they dissociate. So we know that they dissociate. That means they break apart into their ions. Well, the definition of a base is that it dissociates into OH minus ions. So it dissociates into OH minus ions. I just write the minus over the oxygen because that's what's holding the negative charge there rather than leaving it at the end. You can put it anywhere you want. So it dissociates into OH minus ions. The definition of an acid, according to Arrhenius, would be that it dissociates into H plus ions. Why is ammonia, NH3, considered to be a base according to the Bronsted-Lowry theory? Well, according to Bronsted-Lowry, if it accepts or takes a proton from another molecule, then it's a base. So it accepts a proton from another molecule. Accepts or removes there. Calculate the pH of 0.5 molar of hydrochloric acid. Okay, so pH equals minus the log, it's the base 10 of the hydrogen ion concentration. So we have minus log 0.5. And the answer is 0.301 there, or just 0.30. 0.5 molar solution of ethanoic acid. Okay, so I'm not going to go through the whole formula and how to work it out here, but we know that we need the H plus concentration. H plus is equal to root Ka times concentration of Ha. We know that a weak acid doesn't fully dissociate, so therefore we need to see the extent to which it does dissociate. That has to come into our calculation. So that's what Ka there is, the acid dissociation constant. So it's going to be equal to root 1.8 by 10 to the minus 5 times 0.5, and then pH is minus the log of all that. So pH equals minus the log of, so that can go straight into your calculator, 1.8 10 to the minus 5 times 0.5. That is 2.5228, so 2.52 there. That's the calculation at the start. The pH curve shown was obtained when 100 centimeters cubed of 0.5 molar sodium hydroxide was added to one of the 2 acid solutions above. Which of the 2 solutions were neutralized? So I'm just going to zoom in to this to talk about the pH curve. So what happens in a pH curve is you simply add a solution of a base to a solution of an acid slowly and monitor the pH as you go. So what you want to happen in an acid-base reaction is your equivalence point, which is the point at which the base or alkali has completely neutralized the acid, independent of the indicator. That's the equivalence point. Now the end point of the reaction is where you've added a drop of base that has changed the color of the indicator, or a drop of acid which has changed the color of the indicator. So you want the equivalence point and the end point to coincide, which is usually around the middle of the vertical section of your graph. So here you can see that it starts off with a pH, okay, of the acid solution of 2. It rapidly kind of jumps, right, and then it kind of levels off. Now this level off is because you've actually formed a buffer solution, which is an equilibrium system set up when you're adding more base to your acid. But we know that you started around 2.5 for your pH, and then suddenly you go up to around 4 and it stays that way. So this means you started with a weak acid, okay? It finishes up around pH of 13. So this means you're adding a strong base. We know we've added sodium hydroxide. So if the reaction finished at a much lower level, you'd be dealing with a weak base. That would be weak. Likewise, if it started at a much lower pH, you'd be dealing with a strong acid. So which of the 2 acid solutions was neutralized? Here we're going to be dealing with our weak acid. Alright, so the weak acid we used was ethanoic acid. So the ethanoic acid was neutralized. 2 pieces of evidence from the pH curve to support that from your answer. Okay, the 2 pieces of evidence. One, we know this starts at around a pH of 2.5. So the initial pH of 2.5 indicates that it's a weak acid to start with. Another point would be that most of the vertical section here is above pH 7. It's not that it started down here if it was a strong acid. There are two pieces of evidence. Our starting point is 2.5 and the fact that a lot of the vertical section is above 7 there. What's the essential property of an indicator used to detect the endpoint in a titration between this acid and NaOH? So I've mentioned this at the start. The essential point of the property of the indicator between this acid and NaOH is that it changes colour within the vertical section of the graph, i.e. between 6.5 here and 11.5. Okay, so it changes there. That's the essential point of the indicator. So the change of colour coincides with the vertical section. And by that I mean the endpoint and the equivalence point match up. The equivalence point is the end of the reaction. The endpoint is the colour change of the indicator.